All right. Right. Good evening. We'll start. Can you confirm whether I'm clearly audible and visible? Today I also can check from my end. What about the audio and video? It's fine, right? Okay. Right, let's start. Okay. That's fine. All right, we'll start. So today we are going to start from the point that we left off in the last week, right? So last week we started our discussion on meter ruler, on measurements on meter ruler. We started the discussion, right? Recording is not on. Right. All right. Right. So last week we started our discussion on measurements, measuring instruments with the meter ruler, right? And then after that, before starting the vernier caliper, we just checked and we just went through. You got to know what a vernier principle is, right? What a vernier principle is, right? Now, since we are going to start the vernier caliper today, right? We are starting the vernier caliper today from zero, and for the vernier caliper also, vernier principle is needed, right? And not only for the vernier caliper, for all other 4 instruments coming out, starting from vernier caliper, micrometer, screw gauge, sperometer, Downey microscope, in all 4 coming up instruments, the main principle behind that is vernier principle, right? So that's why we discussed about vernier principle separately, right? Now, since it is needed today for the vernier caliper also, right? I'm quickly going to recall what we have done there, and we'll see some example least count findings, right? Least count findings and length findings before we start the caliper. All right. Then listen about the vernier principle. About the vernier principle. About the vernier principle. In a vernier principle, right? In a vernier principle, what's happening is now we had a main difficulty when a measuring instrument is used. The difficulty was we had something called a least count, right? What is least count? Least count is the minimum possible reading that it could take or it can be taken from the instrument. That is for the least count. So if I compare it with the meter ruler, right? Least count of the meter ruler is 1 millimeter. Least count of the meter ruler is 1 millimeter. Least count of the meter ruler is 1 millimeter. Right? Now, any measurement less than 1 millimeter cannot be obtained using meter ruler. Right? So likewise, now when we were thinking about improving the least count means you have to decrease the least count. When the least count is decreased, the accuracy of readings increases. Right? Then, even if the least count decreases, right? If it is not readable by unaided eye, by the naked eye, by the unaided eye, for human beings, for humans, us, that is not going to work out now, right? That's why the scientist called Pierre Vernier came up with this idea initially, with the vernier principle, with the vernier idea, right? In a vernier principle, what is done is there are 2 main scales. There are 2 scales actually. There are 2 scales, and one scale is calibrated in the required unit, and that is called the main scale. And there is a second scale again here in a vernier scale, that is called the vernier scale. Vernier scale is not calibrated, that is divided only, that is divided into small parts, that is only divided, not calibrated. Now, when we check both scales, they are like this, right? When we check both scales, they were like this. We had a vernier scale and a main scale, right? And the main scale was calibrated in a required unit, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say 9, 10. Likewise, now this is calibrated in the required unit. Let's say this, in this particular scale, this is calibrated in centimeters, right? if that is calibrated in centimeters, what's the meaning? If that is calibrated in centimeters, the number here is in centimeters, right? Then the gap between two small divisions here is, if this 1 is divided into 10, that is only 1 millimeter. That's only 1 millimeter. Right? So likewise it goes. Likewise it goes. Right? Then to use alongside with the main scale, a vernier scale is used. Right? Vernier scale is not calibrated. That is divided into divisions. That is not calibrated. Calibrate करना है, divide करना है. And one of the simplest and the most popular vernier scale we have in our labs and in our instruments is 9 to 10 vernier scale. Right? Now for these explanations, I'm again going to use a 9 to 10 vernier scale. Right? 9 to 10 vernier scale means this. What is the idea? 9 to 10 means 9 divisions from main scale. 9 divisions of main scale are coincided with 10 divisions of vernier scale. Right? That is called a 9 to 10 vernier scale. 9 divisions of main scale are going to coincide with 10 divisions of the vernier scale. Right? See, now if I draw the vernier scale here, it is like this. Vernier scale also has a 0, right? Vernier scale has 0, and it goes like this. See, something like this. Now, what has happened is there are only 9 divisions from the main scale. Now, this is my main scale. See, let me label. This is my main scale, and this one here is my vernier scale. Right? Main scale and vernier scale. Now, see, there are 9 divisions from main scale. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 divisions from main scale are coincided with 10 divisions from the vernier scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? That is called a 9 to 10 vernier scale. 9 to 10 vernier scale. Right? 9 to 10 vernier scale. Now, about main scales and vernier scales. When they work together, now what happens is this. When they work together, what happens is, when it is displaced by this gap, that is going to coincide, the first division is going to coincide with the division in the main scale. Right? That's the main idea behind the vernier principle. Right? For that, to get the approach, we need size of, or the length of, one vernier division. We need the length of one vernier division or the size of one vernier division. Right? For that, we can do a small calculation, because we know that always the length from starting point to the end point of the vernier scale and main scale are same. Right? Then with that logic, we can find this out. See, lengths of these two are equal. Lengths of these two should be equal. See, then we know length of main scale equals length of vernier scale. Length of main scale equals length of vernier scale. About main scale we know, because main scale is calibrated in centimeters, which means the gap between two small divisions of the main scale is 1 millimeter. Right? Gap between two small divisions of the main scale is, right? This is something we know, that is 1 millimeter. Then length of main scale from this point to the coincided point, there are 9 divisions. Then it can be written as 9 times 1 millimeter. There are 9 1 millimeter divisions from 0 to coincided point. Right? Just write the length. The length of vernier scale. Let's assume one division of vernier scale as x. If one division of vernier scale is x, right? X times How many divisions? 10 divisions. 10 divisions. Now simplify this. It says 9 or 10 millimeters. 9 or 10 millimeters, which means there is 0.9 millimeters. 0.9 millimeters. Right, which means length of one vernier division. Length of one vernier division of this instrument is length of one vernier division of the instrument is 0.9 millimeters. Right. Now, if you do the math, you can verify this. 1 millimeter into 9 means 9 millimeters. No? Then that 9 millimeter gap is divided into 10. That's why it becomes 0.9. Then 0.9 times 10 is again 9 millimeters. Because their lengths are equal. Right? These lengths are equal. From starting point to the end point. Huh? From starting point to the end point of the scales, their lengths are equal. From starting point to the end point. Right? From starting point to the end point, their lengths are equal. Right? Simple as that. Now, one division is no 0.9. One division is 0.9. Then the next idea behind a vernier scale was this. Listen carefully. Next idea behind a vernier scale was this. Now, if this vernier scale is moved as this first division is coincided, as this first division, no? There are 10 divisions of 1, 2, 3, 4, likewise. There are 10 divisions. Now, if it is moved as this first division is coincided, we know if this part is 1 millimeter and if this part is only 0.9 millimeter, that gap in between is 0.1 millimeters. No? That is 0.1 millimeters. Then if we move the scale as it to coincide the first division, which means the distance I have moved is 0.1 millimeters. Distance I have moved is 0.1 millimeters. If you consider the same for the second division, up to second division through the main scale, the length is 2 millimeters. 2 millimeters. Now, if I coincide the second division of my vernier scale, right? Second division of the vernier scale is 0.9 times 2, 1.8 millimeters. Then the gap is 0.2 millimeter. Then if my second division is coincided, distance traveled by the vernier scale is 0.2. If the third division is coincided, distance traveled by the vernier scale is 0.3. If the fourth division is coincided, 0.4. So likewise, now nicely, it goes when we are trying to move this or slide this alongside the main scale, right? Which means now we are capable of reading out or taking out 0.1 millimeter readings now, because when the first division is coincided, the reading was 0.1 millimeters, right? Reading was 0.1 millimeters, which means 0.1 is readable now. 0.1 is readable. 0.1 is readable. 0.1 is readable means the least count has reduced to 0.1, because minimum reading that we would take is the least count. Now, from this setup of two scales, right? From this different idea, right, of two scales, 0.1 is readable, which means least count is reduced to 0.1 millimeters, right? Least count is reduced to 0.1 millimeters, right? So likewise, now we have reduced the least count of the instrument, but yet we are not using 0.1 millimeter divisions. That's the advantage behind this. We are still using 1 millimeter and 0.9 millimeter divisions. They are visible. They are very much convenient to the eye. They are visible to the eye, visible to the unaided eye, right? But yet we are reading out least count like 0.1 millimeters. Right? We are reading out a least count like 0.1 millimeters. Right? This concept is called the vernier principle. This concept is called the vernier principle. Right? Now, from this, now if first division is coincided like this, first, second, these are the divisions, third, fourth, fifth, and so on. If first division is coincided, the distance moved is 0.1 millimeters. The second division is coincided, distance moved is 0.2 millimeters. If the third division is coincided, distance moved is 0.3 millimeters. For the fourth division, 0.4 millimeters. And for the fifth division, 0.5 millimeters. Likewise, it goes on. Right? Now, after this, we actually found this. We found the least count of the instrument using two ways. Right? We'll quickly Record it. Give me 1 second. So switch the mic. Okay. Right. Okay. So likewise, the gaps can be determined. And for the least count now, we came up with the equation. Right? For the least count, we came up with an equation. It was like this. There were two equations actually. There were two equations. Right? First equation we came up for the least count was least count of the instrument is the gap between these two divisions. No? Then one division of main scale minus one division of vernier scale. Right? That is one of the equations. Least count can be written as one division of main scale minus one division of vernier scale. One division of main scale minus one division of vernier scale. Then can be written as now if we need to find it. We need to find it. We need to find it. This is how we could find it. Then least count is one division of main scale. What's that? 1 millimeter. 1 millimeter. Minus one division of vernier scale x 0.9 millimeters. See, it says then 1 minus 0.9 means 0.1 millimeters. Right? Least count of the vernier scale now is least count of this vernier scale now is 0.1 millimeters. Least count of this vernier scale now is 0.1 millimeters. For the same thing, we had another equation. We got another equation that goes like this. Least count can also be written as one division of main scale. One division of main scale. One division of main scale over number of vernier scale divisions. Number of vernier scale divisions. Number of vernier scale divisions. Right? This is also a possible equation. Right? I have to know both the equations because with the availability of data, we have to pick the correct equation or the proper equation that matches the given conditions. Therefore, you have to know both. Right? Have to know both. You have to know both. Both of them do the same. It does the same. But with the availability of data, we have to pick the correct ones when it comes to questions. Okay. Then if I apply here, right? Least count equals one division of main scale was 1 millimeter. One division of main scale 1 millimeter. Then number of vernier scale divisions. How many? 10 divisions in vernier scale. Then 10. Then it also says 0.1, 0.1, 1 order 0.1 millimeters. Right? So both ways are correct. Both are fine. Both ways are correct when finding the least count. Right? So this is where we stop our discussion. This is where we stop our discussion last day. Right? This is where we stop our discussion last day. Right now, today we are going to start the vernier caliper. After we'll recover this again with like two exercises, finding the least count and the lengths, right? For the exercise vernier caliper. Now, main plan today is we are going to cover the vernier caliper. Right. Now, if there's anyone who were not there last week, or if there's anyone who is joining today as the first day, right? If you are a newbie to the class, right? If anything to take down, right? I can give you like 2 minutes. If there's anything you can take down. Take down it. anything and ask if any questions and clarifications needed before we move on. So your video is not clear. No, my video is clear. I'm checking my video. Check your connection. Right. So do we have to state the Vernier principle in words in questions? No, it won't be asked that way. Right. Only the sums are coming. Right, sums are coming. All right. Then from this, let's practice like 1 or 2 exercises before we start the caliper. Right. Take this down as exercise 1. Take this down as exercise 1. Exercise 1. Exercise 1. Exercise 1. Write down 19 main scale divisions. Exercise 1 now. Exercise 1. 19 main scale divisions. 19. 19 main scale divisions. 19 main scale divisions. 19 main scale divisions of 1 millimeter. 19 main scale divisions of 1 millimeter. 19 main scale divisions of 1 millimeter. Of 1 millimeter. Coincide with. Coincide with. Coincide with. Coincide with 20 vernier scale divisions. Coincide with 20. Coincide with 20 vernier scale divisions. Right? Coincide with 20 vernier scale divisions. Coincide with 20 vernier scale divisions. 20 vernier scale divisions. Right? find the length of one division of vernier scale. Find the length of one division of vernier scale. Find the length of one division of vernier scale. Find the length of one division of vernier scale and the least count. And the least count. Right? Questions are I need one division of vernier scale. I need one division of vernier scale and the least count. Right. 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 Let's see. I will start into one right. And share your answers. Share your answers. Once on YouTube also, you also can put your answers to the live chat so I can see. All right. One division of vernier scale and the least count. Right. Send your answers to main chat if you want to. It's a 19 to 20 vernier scale. 19 to 20. 19 to 20. 19 to 20. So we are in measuring instruments. We are in measuring instruments and from unit 1, measurements, there are two main parts. One is units and dimensions that we finished in July. And now we are in measuring instruments. That's the second part. And both parts are very important in the unit. Right? Both parts are very important and this is actually the second half. This is actually the second half. Right? The ones who join today or new, you can get the previous recordings if needed. That is from the month of July. Right. What about the answers? Length of one division 0.95 millimeters. It is correct. Good. Length of one division 0.95. That is correct. Good. All right. Let's see. 19 to 20. Right. So we know in any vernier scale, right? Always the lengths are equal. in a vernier scale, lengths are equal. Length of the main scale equals to length of vernier scale. That is when it is coincided to one division. Right? Which means length of 19 divisions of the main scale here on this one is equal to length of 20 divisions of the vernier scale. Simple as that. Simple idea is that. Then we are starting from here again. Length of main scale equals length of vernier scale. Length of vernier scale. Length of main scale equals length of vernier scale. Right? Length of main scale equals length of vernier scale. Now, there are 19 divisions of main scale. I clearly gave you that in the question. There are 19 divisions of 1 millimeter. 1 millimeter divisions. 19 1 millimeter divisions. Then the length is 19 millimeters. Which means this is how you should present it. 19 1 millimeter divisions. 19 1 millimeter divisions. Length of vernier scale. Let's assume length of a vernier scale as x, right? If length of a vernier scale is x, right? There are such 20 divisions. No? There are such 20 divisions. Then the total length is x into 20. Total length is x into 20. Now x is given by 19 over 20 millimeters. 19 over 20 millimeters. Simplify this. This is 0.95 millimeters. This is 0.95 millimeters. 19 over 20 is 0.95. So that is 0.95 millimeters. The length of this vernier scale is 0.95. When you find the least count, you better find the least count in both ways, right? Since you are still practicing from today, right? Then when we move on, you can pick the easiest equation and go there, right? But today, to practice both the equations, you better show the least count. It should be same. Either way it is same. It is definitely same. But you better show it in both ways for your understanding and for your evidence. Right? Then 0.95. When you find the least count, then least count is 1 division of main scale minus 1 division of vernier scale. 1 division of main scale is 1 millimeter. 1 division of vernier scale is 0.95 millimeters. Right? Then least count of the instrument is 0.05 millimeters. 0.05 millimeters. 0.05 millimeters. Or else you can use the other equation. You may use the other equation. 1 division of main scale over number of vernier divisions. Number of vernier scale divisions. 1 division of main scale is still 1 millimeter. 1 division of main scale is still 1 millimeter. Number of vernier divisions here 20. Right? 1 over 20. 1 over 20 is 0.05. 1 over 20 is 0.05. 1 over 20 is 0.05, not 0.5. Not 0.5. That's a subtraction error because your length is correct. Then if the least count is wrong, which means there is a simplification. 0.05. Then final answers. Length of one vernier scale is 0.95. 0.95 and the least count 0.05. Right? When it comes to the accuracy of readings, that is going to take from this. Right? When it comes to accuracy, we know smaller the least count, higher the accuracy. So therefore, this scale is more accurate compared to 920 scale. Scale is more accurate compared to 920 scale because least count of this scale is even smaller. Least count of this one is even smaller. Right? Mention below with the red pen. 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 Put an asterisk mark and mention with the red pen. Smaller the least count. Smaller the least count. Smaller the least count. smaller the least count, smaller the least count, higher the accuracy. 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 Right? Smaller the least count, higher the accuracy. Right. Let's see another one. Let's see another one. Exercise 2, number 2. Number 2, write down. Number 2, write down. Number 2, write down. 99 main scale divisions. 99. 99 main scale divisions. 99 main scale divisions. 99 main scale divisions of 1 millimeter. 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 99 main scale divisions of 1 millimeter coincide with coincide with coincide with coincide with 100 divisions of vernier scale. 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 100 divisions of vernier scale. Coincide with 100 divisions of vernier scale. Determine length of a vernier division. Determine length of a vernier division. Determine length of a vernier division. Length of a vernier division. Determine length of a vernier division and please count. Right? Length of a vernier scale division and the least count. Right, start now. Feel free to ask if any questions. right? Getting some answers. Right. Length of conductor 0.99. Pitch count 0.01. Right. Right. Let's see. Right. I mean, let's see. Now here also when you find the least count, you can find using both ways to get the idea. Right? We are find using both ways to get the idea. Right. 99, 100 scale is given. Right. So whatever the scale given, we know always length of main scale equals length of vernier scale. Right? Always length of main scale equals length of vernier scale. Right? Then we start from here. Length of main scale equals length of vernier scale. Length of main scale can be written as 1 millimeter into 99 because 99 divisions are coincided. Length of vernier scale, if one division of vernier scale is x, such 100 divisions. Then x equals 99 over 100 millimeters. 99 over 100 millimeters. Right? That is 0.99 millimeters. 0.99 millimeters. Right? One division of vernier scale is 0.99 millimeters. One division of vernier scale 0.99 millimeters. 0.99 millimeters. Right? 0.99 millimeters. Then let's count. There are two ways. Let's count. Then either you can write the least count as one division of main scale minus one division of vernier scale. One division of main scale is 1 millimeter. One division of vernier scale is x 0.99 millimeters. Right? Then least count is 0.01 millimeters. 0.01 millimeters. Now, if you compare with the previous scale, right, this least count is even smaller. This least count is even less, even smaller, which means higher accuracy. Right? Smaller the least count, always smaller the least count, higher accuracy. Smaller the least count, higher accuracy. Right? Likewise, when number of divisions in vernier scale increases, right, least count decreases. When number of divisions in vernier scale increases, least count decreases. and it increases accuracy. And it increases accuracy of the scale. It increases accuracy of the scale. Right? Okay, then if you use the other equation, least count is also written as one division of main scale over number of vernier scale divisions. One division of main scale 1 millimeter. Right? Number of vernier scale divisions 100. Right? Still you get 0.01 millimeters same. 0.01 millimeters. 0.01 millimeters. Right. Okay. Check if any changes with your answers. Right, and correct them. Check if any changes with your answers and correct them. Right. Right, all good. Is it all clear up to this point? Any questions? Is it all clear up to this point or any questions? If anything, feel free to ask. If any questions, anything. And just tell me it's clear. If it is clear enough and the answer also, you can raise your hand if clear enough. Raise your hand if clear enough. Okay. What about others? Right, okay. All right, then we'll move on. And one point to be mentioned. Mention this point in red. After all, mention this point in red. Mention. Higher the number of divisions in vernier scale. Mention below in red. Higher the number of divisions in vernier scale. 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 Smaller the least count. Clear. Okay, good. Smaller the least count. And higher the accuracy. 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 All right. Then let's get into our thing today. Put the heading as vernier caliper. Put the heading as vernier caliper. Vernier caliper. Vernier caliper. Vernier caliper. Vernier caliper. Right. So as I told you, under measuring instruments, we will be discussing about 5 measuring instruments, right? 5 measuring instruments, starting from meter ruler, vernier caliper, sperometer, micrometer screw gauge, sperometer, traveling microscope, right? Those are the 5 measuring instruments to be discussed, right? And about meter ruler we completed last week. Meter ruler we completed last week. So today we are starting the vernier caliper second out of 5. Second of 5. Right? We are starting the meter ruler second of 5. Second of 5. Right? Listen, when it comes to meter ruler, sorry, when it comes to vernier caliper, the meter ruler, when it comes to vernier caliper, right? Vernier caliper is also mainly used to measure lengths, right? That is mainly used to measure lengths, right? But other than that, other than measuring the length, there are some specific cases, specific readings that we can take from vernier calipers, right? But they are all length readings, length-related readings, length-related readings, right? But they are basically going under the category of lengths, right? First, before we identify the parts, first I'll show you how this is going to work, right? First I'll show you how this is going to work, right? And then we'll identify the parts and we'll see what's happening here with the functionality mechanism and the task of each part. Now, it is unlike a meter ruler, so you can see there are some different parts that you might don't know, you might not know. See, there are different parts. This is called the vernier caliper. This is called the vernier caliper. Right? Sometimes some of you might have seen this. Sometimes some of you might have seen this. Right? Sometimes not. But when it comes to an instrument like meter ruler, or almost all of you have seen, because that's a very regularly using and very popularly using instrument. When it comes to the other 4 instruments coming up, starting from the vernier caliper, that is not as popular as the other instruments like meter ruler when it comes to our household usages. Right? In labs we have, but in our day-to-day life we don't use such ones. There are people who use these ones also, but majority is not using in day-to-day life. Right? Majority is not using in day-to-day life. Right? So here, what's happening is like this. First, before explaining the mechanisms, right? First let me introduce you the parts here, right? Because I'll be using these terms when I introduce the mechanisms hereafter, right? Okay, so basically, this instrument is called a vernier caliper, right? It is called a vernier caliper. Here, you can see, only one part is movable. See, only one part is movable. And this part is fixed. This is fixed. See, this is fixed. And only this slides on this one. Right? Right? This part is fixed. And only this one slides. Only this one slides. Right? So therefore, we call this fixed part the fixed jaw. Right? We call this fixed part the fixed jaw. JAW jaw. Right? Fixed jaw. Right? And this sliding part we call sliding jaw. Right? Fixed jaw and the sliding jaw. Right? Simple. Fixed jaw and the sliding jaw. Fixed jaw, sliding jaw. Fixed jaw is fixed, as the word says, and the sliding jaw is moving. Sliding jaw is moving. Right? Fixed jaw and the sliding jaw. And about these jaws, right? There's a pair. Here's a pair. Here, see, this pair is called external jaws. This pair is called external jaws. Because the purpose is external jaws are going to tie with the object from the external side. See, it is going to tie up with the object. It is going to firmly keep the object like this from the external side. From external side. Let me show you from this. See, now it is going to firmly keep the object in between from the external side. Right? That's why it is called the external jaws. Right? So these two are external jaws. Then these two, you can see now. See, there are two small jaws here. Two other small jaws here. Right? Two other small jaws here. Right? Sometimes make it focus very. Right, Ben. These two, the two small jaws, right? Small jaws, right? They are called internal jaws, right? Now it is focused, right? They are called internal jaws. Right? Make an scale I close up a pen after explaining. I'll show you close up again. Right? We'll show you close up again. This is internal jaws. Internal jaws means internal jaws are keeping objects firmly in between using the internal side or internal surface. Right? Like this. From the internal surface. Then say this one. This one. See? Now here there's a hole inside. Now when this is firmly kept using internal jaws, see, this is how it is. Internal jaws are going to keep objects firmly, tightly in between jaws from the internal surface. And the external jaws are going to keep these objects firmly in between from the outer surface or the external surface. So they are called the internal jaws. These two are called the external jaws, right? And this one, this whole thing is called the fixed jaw. This whole part is called the sliding jaw, right? Now I have introduced 4 parts. Now I have introduced 4 parts so far. And then here you can see a nut kind of something, no? Here we have a small nut kind of something. Nut right? That is actually not a nut, right? That is a lock. That is a lock. Now what happens is when this is rotated, see, now this is locked, right? When this is locked, this cannot be moved. This cannot be moved. When this is rotated the other way, it is unlocked. When it rotates the other way, it is unlocked. Now it is movable, right? So the purpose of the lock is to keep this without moving until we finish taking a measurement. And otherwise, when we are taking measurements, if this slides here and there, we are going to make an error in the reading that you are going to take now. Right? That's why this kind of a mechanism is a locking mechanism is there. Right? That's why this kind of a locking mechanism is there. That's a locking mechanism. It's a lock, basically a lock. Right? Lock. Make a move around. Right? When this is unlocked, it can be moved. Right? Simple as that. And here you can see another small wheel kind of a thing. Right? Like a wheel. Right? That we call the nut. Right? The purpose of that is, right? We keep our thumb there like this. We keep the thumb there, and easily we can slide the sliding jaw from the fixed jaw like this using the thumb, right? So that is for the purpose of keeping the thumb like this. This is how we use the instrument. You have to grab this by the thumb if you are using this way, right? Now since I wanted to show you, that's why I showed you this way. Otherwise, when I'm using the instrument, this is how we use. Always we keep the scales towards user, right? We keep the scales towards user like this. See? This is how I use. Then easily from this wheel we can move this here and there using the thumb. Right? Thumb use kara, make a move kara. Thumb use kara, move kara. Like that. Then the main part here is the scales. Listen, main part here is the scales. Right? I think it is visible to the camera. Right? Now here, okay, now it is focused now. Here you can see a main scale. You can see the scale. This is the main scale. Right? Method scale up on. Here you can see a scale. This one is the main scale. And here at these two sides of the small part here, in the main part again, right? There's another small scale goes. Can you see? There's another small scale goes here. See? There's another small scale goes here. That small scale is called the vernier scale. That small scale is called the vernier scale. Right? Then this part is the main scale, and this one is the vernier scale. Main scale and the vernier scale. Right? Hope it's clear. Then from the vernier principle we learned just before. Right? From the vernier principle you learned just before. Now this is how the vernier principle is applied in the vernier caliper. Right? This is how the vernier principle is applied in the vernier caliper. Right? This part is calibrated with the main scale, and this is a vernier scale, right? This is a vernier scale, and the last part here is this, right? Sometimes you might notice that when this sliding jaw is slit, see, when this sliding jaw is slit, there's another part coming out from here. See, there's another pin coming out from here. There's another pin coming out from here. See, it is connected to the sliding jaw and it works with the sliding jaw. See, it works with the sliding jaw. There's a pin and it works with the sliding jaw. Can you see? It works with the sliding jaw. It works with the sliding jaw. So this is called the depth measuring rod or depth measuring pin. That is called the depth measuring rod or depth measuring pin. Then, as the word suggests, it is to measure depths. It is to measure depth because this small part can put into holes, can put into small holes, and their depths can be measured. It can be put into small holes like this and small holes like this, and their depths can be measured. Right? Now again, if I explain the parts, right now all parts are explained. Now again, I'm going to revise. This one is called the fixed jaw. This one fixed jaw, right? And this one, this part, sliding jaw. This part, sliding jaw, right? And these two, external jaws. These two, internal jaws. Right? And this one, lock. This one, nut. And here, main scale. This one, vernier scale. And here, depth measuring rod. Right? So these are the all parts of a vernier caliper. But I didn't explain the functionality of each part yet. Right? We'll explain the functionality next. Right? This is just the parts, identification of parts of the vernier caliper. Right? Then after that, we'll see for which purpose these parts are here for. Right? That's the purpose of the functionality. Right? This is just the parts. Okay, now we'll take it to your notebook and go to label. We'll label, and then I'll be explaining again after labeling. Right? Now let's draw this and label. Right. Now you can take this down with me. Right, I'm going to do this. Now you have to draw a vernier caliper. Right? How to draw a vernier caliper. You also can take it down along with me, right? Because now for this drawing, it might take some time, right? So therefore, you also can take it down along with me. That is better. Right? You also can take it down along with me. Right? Take it down along with me. Right. Scales are here. Scales are here. Right. Right. Let's label. Let's label the marks. This one, fixed jaw. Right. Fixed jaw. And I have from the lock. Lock is here. Locking mechanism, lock. And the nut is here. Right. Then this one, fixed jaw. This one, fixed jaw. Fixed jaw. Right. This sliding jaw. Sliding jaw. Right. These two are called external jaws. External jaws. External jaws. Right. Then these two are called internal jaws. Right. External jaws are also called outer jaws. Internal jaws are also called inner jaws. Right. Both are fine. Both are fine. Right. It is internal jaws. Right. And this part, lock. Lock. Right. And here, this one, vernier scale. Right. This one, vernier scale. Right. And here, this is the main scale. Main scale. And here, this one is called the nut. 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 And here, this one, depth measuring. Rod, or that is also called depth measuring pin. Right. So likewise, right, take it down, and label marks and check your marks whether it is labeled properly. Right, take it down and check the diagram. Double check your diagrams because that is very important. Double check your diagrams whether it's correct. Double check your diagrams whether it's correct. Very important. Right? Right. Finish. Right. Okay. Then let's see. Let's see what are the functions, what's the purpose of having these parts and the measurements that we are going to take and how to take measurements, right? And there are errors when taking measurements, about errors, right? Those are the parts coming up in the discussion now, right? First point. Now you can take down the note in point 4. Right? First point. First point. Write down first point. Write down. Vernier caliper is mainly used. Vernier caliper is mainly used. Vernier caliper is mainly used to measure. Mainly used to measure. Mainly used to measure external diameter. External diameter. External diameter. Come on. Internal diameter. External diameter, come on, internal diameter. Come on. Depth of a hole. Come on, depth of a hole. Depth of a small 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 hole. And thickness. And thickness. Thickness of an object. Thickness of an object. And thickness of an object. Right? Right? Next point. Next point. Main scale of vernier caliper. Main scale of vernier caliper. Main scale of vernier caliper. Main scale of vernier caliper is calibrated in. Main scale of vernier caliper is calibrated in. Main scale of vernier caliper is calibrated in centimeters. Calibrated in centimeters. Main scale of vernier caliper is calibrated in centimeters. And length of one main scale division and length of one main scale division and length of one main scale division and length of one main scale division. Length of one main scale division is 1 millimeter. Is 1 millimeter. Length of one main scale division is 1 millimeter. Length of one main scale division is 1 millimeter. Right. Listen now. Before writing, listen. Now, when it comes to vernier calipers, right, there are vernier scales with 9 divisions, 9 to 10, I mean, 9 to 10 divisions, or 19, 20, 49, 50, and 900. There are different scales, right? Most popular one, the frequent popular one that we use in our labs is 9 to 10 scale, right? The popular one is 9 to 10. That doesn't mean the only one is 9 to 10. That is not the case. Popular one is 9 to 10. That does not mean the only one is 9 to 10, right? It can be anything as 9 to 10, 19, 20, 49, 50, 9900. But in the schools, in the school labs, the popular one we have is 9 to 10, and you are getting most of the questions are also from 9 to 10, right? So therefore, about the typical one we can say that is a 9 to 10 scale. Right. Next point. Next point. Vernier scale consists of 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 10 divisions. Vernier scale consists of 10 divisions. Vernier scale consists of 10 divisions. In a typical vernier scale, vernier scale consists of 10 divisions in a typical vernier scale. Right? Vernier scale consists of 10 divisions. Let it be vernier scale. Right, next point. Next point. Next point. 9 divisions of main scale. 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 Coincide with 9 divisions of main scale. Coincide with 10 divisions. 10 divisions in vernier scale. Coincide with 10 divisions in vernier scale. In a typical vernier caliper. In a typical vernier caliper. In a typical vernier caliper. A typical vernier caliper. Right. Now, if there is a 9 to 10 scale, that is a popular scale that we have found before. And if there is a 9 to 10 vernier scale, we know, then one division of vernier scale is going to be, right, in that 9 to 10 scale, right? Then one division of vernier scale. One division of vernier scale is going to be 0.9 millimeters, no? Right? And the least count of this 9 to 10 scale is we found before, the least count is 0.1 millimeters. Right? Mention these two below. Mention these two below. Right? One division of vernier scale is 0.9 millimeters, and least count of the scale now is 0.1 millimeters. 0.1 millimeters. Right. Right. Next point. Objects to be measured. Next point. Objects to be measured should be kept. Objects to be measured should be kept firmly in between. External jaws or internal jaws. Should be kept firmly in between. External jaws or internal jaws. Should be kept firmly in between. External jaws or internal jaws. External jaws or internal jaws. Right? Next point. Lock is used to. Next point. Lock is used to. Stop the motion. Lock is used to stop the motion. Of sliding jaw. Stop the motion of sliding jaw. Lock is used to stop the motion of sliding jaw until we finish taking a measurement. 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 Okay. Right. Now let's see how the readings are taken. Let's see how the readings are taken from this. And as a next subheading, write down. Next subheading. Taking readings using vernier caliper. Subheading taking readings using vernier caliper. Taking readings using vernier caliper. Taking readings using vernier caliper. Right. Below that, write down. Below that, write down. Let's consider. Below that, write down. Let's consider. Let's consider a vernier caliper of which. Let's consider a vernier caliper of which. Let's consider a vernier caliper of which 9 main scale divisions are. 9 main scale divisions are coincided with. 9 main scale divisions are coincided with. 9 main scale divisions are coincided with 10 vernier scale divisions. 9 main scale divisions are coincided with 10 main scale divisions. 10 main scale divisions. Right? 9 divisions of main scale are coincided with 10 main scale divisions. Okay. Look at the board now. Now I'm going to draw a random position of the scales when we measure something. Right? I'm going to draw a random position of the scales here. Random position of the scales when we measure something. Random position when we measure something. Right? Do it here. Now, main scale. These are random positions of the scales. Right? Main scale. Let's say here we have 3. Then 1, 2, 3, 4, 5. 1, 2, 3. So likewise, that's a main scale. That's a main scale. And the vernier scale here is like this. Vernier scale here is like this. Vernier scale. See? And the vernier scale. Right. See? Now, this is a random position. This is a random position of the scales when we measure something. Random position of scales when we measure something. Right. Look at the board. Look at the board. Now, let's say this is our main scale. And this is the vernier scale. This is a vernier scale. Right? When we take a reading, right? This is how we take a reading. Listen carefully. Listen carefully. Listen carefully. We know. Now, up until this point, before vernier 0 starts, listen, up until this point, before vernier 0 starts, there's a number of, right? There's a number of divisions completed from the main scale. There's a number of divisions completed from the main scale before vernier 0, right? And there's another value of the vernier scale that is given from the vernier scale, right? Now, from our vernier principle knowledge, we know how to read the vernier scale, how to read the reading from a vernier scale. Now, in this case, before the vernier scale, there's a part already completed now. So therefore, when you read something from a vernier scale, listen carefully, this is a general idea. When we read something, when we take a reading from a vernier scale, right? Always that reading is coming as the sum of main scale reading plus vernier scale reading. Right? Always the reading is coming as, always any reading is coming as, right? The sum of main scale reading plus vernier scale reading. Main scale reading plus vernier scale reading. Right? Listen carefully. Main scale reading is the completed main scale before vernier 0. Completed main scale before vernier 0. Vernier 0 is here. See, vernier 0 is here. So before vernier 0, up to this division, main scale is completed. Up to this division, main scale is completed. Before vernier 0. Before vernier 0. Then this 3 means 3 centimeters. No? 3 here means 3 centimeters. And we know 3 centimeters means 30 millimeters. And the gap between two divisions in the main scale is 1 millimeter. Then what's the number of completed divisions here in the main scale? 31. 31. Always you have to get the number of divisions completed from the main scale before vernier 0 starts. Before vernier 0 starts. Right? 32 is not completed because vernier 0 has started before. Right? Then main scale means, repeating again. Main scale means the number of divisions completed from main scale before vernier 0. Right? Number of divisions completed from main scale before vernier 0. Before vernier 0. Then in this particular scenario, see, number of divisions completed from main scale is 31 millimeters. Right? It is easy to convert to millimeters because vernier scale is coming from millimeters. Vernier scale is also coming from millimeters. Right? Therefore, it is easier to convert that into millimeters. That is easier to convert. That's why I wrote it as 31. 3 means 3 centimeters, 30 millimeters. And this point 1 millimeter, 31. Then go to the vernier scale. Vernier scale is red dash, right? Vernier scale is red dash. Number of coincident divisions. Number of coincident divisions into least count. Number of coincident divisions into least count. Right? From the vernier principle, we got the idea. If one division is coincident, that is 0.1. Two divisions, second division means. Second division means 0.2. If the third division is coincident, 0.3. Fourth, 0.4. So likewise it goes to. That's why we can say it easily as an equation as the number of coincident division into least count. Then from the vernier scale, first let me write it as an equation for your reference. Here main scale reading and the vernier scale is red dash. Number of coincident divisions. Number of coincident division times least count. Times least count. Right now, if I take the reading, from main scale 31 millimeters completed. From the vernier scale, coincident division. See, coincident means there should be one division that is falling on or laying on one main scale division from this vernier scale, right? And there's only one such division in any vernier scale. Right? Only one division will be coincided at a given time. That's how vernier scales are made. Only one division will be coincided at a given time, at any given time. Then, see, first one is not coincided, second one is not coincided, third is coincided, see, and rest is not coincided. Third is coincided. Then, number of coincided divisions, 3. Number of coincided division, 3. Then least count is the typical scale 0.1 millimeters. 0.1 millimeters. Then the reading is coming as, see, R equals 31 millimeters plus from here 0.3 millimeters. So the final reading is 31.3 millimeters. 31.3 millimeters. Right, final reading is 31.3 millimeters. And my reading is now taken up to 1 millimeter decimal. Right? So that's the advantage. Right? Because now, since the least count is less, right? We have got the capability. Of taking a reading to 1 decimal place. Then final reading is 31.3 millimeters. Right. Now, this is the main equation we use. So you better highlight the equation. when you take down, you better highlight the equation when you take down, right? And then take the reading. Then take the reading, right? So I hope it's clear enough. If any questions, feel free to ask, right? Or else you can take it down and your scale diagram, this one scale, your scales diagram should be exactly as same as mine. Right? Otherwise, it changes. Your diagram should be exactly as same as mine. And the third division here, third division will be coincided. And zero should be starting somewhere in between 1 and 2 here, 31 and 32. Right. Simply, your diagram should be exactly same as mine. Okay. Take it down. Take it down. Right. Okay. Right down below. Right down below. First point. First point. Main scale reading is first point. Main scale reading is 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 the completed number of main scale. Main scale reading is the completed number of main scale reading is the completed number of main scale reading is the completed number of main scale divisions. Completed number of main scale divisions. Before vernier 0 starts. 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 Underline no highlight 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 before vernier 0 starts. Before vernier 0 starts. Before vernier 0 starts. Right. Next point. Next point. Vernier scale reading is next point. Vernier scale reading is vernier scale reading is vernier scale reading is the number of coincided vernier division is the number of coincided vernier division is the number of coincided vernier division number of coincided vernier division times least count. 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 Right? Number of coincided vernier division times least count. Okay, simple as that. Simple as that. Right, now I will give you another example for you to read out. Right, so we move on. Right, we will give you another example to you to read out. Right, now try to take the reading here. Right, now this is an example. This is an example. I need you to take the reading here. Right, take the reading here and tell me. Try this one. Try this one. Try this one. Take the reading here of this scale. Take the reading here of this scale. Take the reading here of this scale. Right? 8. Take the reading here of this scale. You can send your answers. You can send your answers. Right? Send your answers to the chat. Whatever it is. Right. We are getting answers. Right. We are getting answers. 77.6 millimeters. 77.6 millimeters. Right. Okay. See, reading is right simple. Always any reading of a vernier scale is given by the sum of main scale reading and vernier scale reading. Right? Sum of main scale reading and vernier scale reading. Right? Then any different answers before I start? 77.6. Are there any different answers? No. 77.6. Okay. Then about the vernier scale reading. Vernier scale reading is always number of coincided divisions. Number of coincided division into least count. Number of coincided division into least count. Right? Then from main scale. Main scale reading is I clearly said that main scale reading is the completed main scale before vernier 0. Completed main scale before vernier 0. Vernier 0 is here. Vernier 0 is here. Right? Vernier 0 is here. This is 8. 8 means 8 millimeters. 8. Then this is 79 millimeters. This is 78 millimeters. 78 is completed because that is before vernier 0. Right? This is not vernier 0. Vernier 0 is here. This is just the edge of the vernier scale. Vernier 0 is here. So completed main scale is not 77, that is 78. That is 78. That is 78. Completed main scale is 78 millimeters. Right? Completed main scale is always the completed divisions of the main scale before vernier 0. Before vernier 0. Right? I asked you to highlight also. Before vernier 0. Right? Then that is 78. That is 78. Then coincided division. of the vernier scale 1, 2, 3, 4, 5, 6. 6 into least count 0.1 millimeters. And the final reading is 78.6 millimeters. 78.6 millimeters. Got it? 78.6 millimeters. Right now, if you didn't count the complete main scale properly, right, you might have got 77.6. Right? So I'm repeating again. Main scale, complete main scale means main scale divisions before vernier 0 starts. Right? Vernier 0 is the keyword here. Main scale divisions before vernier 0 starts. Right? It should be main scale divisions before vernier 0 starts. I hope it's clear now. I hope it's clear now. Right? So that's the thing. That's the thing. That is what you highlighted. And that's why I highlighted it. Right? This is just the edge. I caliper right? The edge of the vernier scale and 0 of the vernier scale are at 2 different points. Right? Edge and the 0 of the vernier scale are at 2 different points. Right? Edge and the 0 are at 2 different points. Is it visible? Right? Edge is here. Edge of the vernier scale is here. See? Focus on edge of the vernier scale is here. And 0 is a little bit left to that point. See? Right? Edge is different. And 0 is different. Edge is 0. Right? So what you need to consider when taking the main scale reading is where the vernier 0 is. That is where the vernier 0 is. Right? Because it depends on that. It depends on that. Right? You have to consider where the 0 is. Right? That's it. Listen now. Listen. Now, if I quickly show you how we are taking readings using this. Right now, as a sample object, I'm going to use this lid. Right? As a sample object, I'm going to use this lid. What lid? That here. Right? Say I need to get the external diameter of this lid. Right? Then what we do is you have to keep it tight between the external jaws of the vernier caliper like this. If you need to measure the external diameter, right? If you need to measure the external diameter, you have to keep it tight between the external jaws of the caliper like this, right? To measure the external diameter. And then until we finish taking the measurement, we are locking the instrument. Now when the instrument is locked, now it is not going to move. That is not going to move. Now you can take the reading from here. Right now, here a reading is shown. Here reading is shown. Here reading is shown. See from the main scale. Now in this case, 29 is completed from the main scale. Right, 29 is completed from the main scale, and from the vernier scale, exactly 5 is coincided. Right, 29 is completed from the main scale, and 5 is coincided from the vernier scale. Then the reading is 29.5 millimeters. 29.5 millimeters. So likewise, you can measure the external diameter using external jaws. Right? You can measure the external diameter using external jaws. Right? Read now here you can see the reading. Here you can see the reading. Right? Is it focused? Okay. See? Right. See? Now when this is kept firmly in between, now you can see the reading from here. Now you can take the reading. You can take the reading. Right? Can take the reading from here. See? Now main scale is here. Complete number of main scale divisions you can see. Right? Vernier scale is here, vernier scale is done. So what we are going to be is something like this. And from this, the reading is taken. Right? From that reading is taken, and that is the external diameter of this lid now. That is the external diameter of the lid now. Say you need to take the internal diameter. You need to take the internal diameter of this ring. You need to take the internal diameter of the ring. To take an internal diameter, you have to use internal jaws. Right? Then unlock this, release, and you can take it out. And now if I need to measure the internal diameter, I have to keep it firmly, tightly in between or internal jaws like this, right? And put on the lock. See, now it is tightly kept between internal jaws. Right, now that is tightly between internal jaws. Right, now take the reading again. Now from the main scale, 25, 26 completed. From the main scale, 26 divisions are completed. From the vernier scale, 4 is coincided. From the vernier scale, fourth division is coincided. Then 26.4 millimeters. Right? 26.4 millimeters. Correct. So that's the beauty. 26.4 millimeters. Right? Reading an external diameter and an internal diameter using the vernier caliper. Right? Then let's say you need to measure a depth. Right? Let's say you need to measure a depth. Right? If you are measuring a depth, what you need to do is, right? You have to let this, right? Now I don't have a hole to show it. Right? You have to put this rod, depth measuring rod, into the hole like this, right? Make assume current, or let's assume this as a hole that you are going to measure. Then you can insert this rod into the hole that you are going to measure. Right? You can insert this into the hole you are going to measure and lock the instrument and take the reading from here. Then this part is measured, that is the depth of the hole. If this part is measured, that is the depth of the hole. Right? So likewise, you can take any required measurement. Say you need to take a thickness of something. Thickness at the beginning I told you, this can be used to measure thickness also. Right? Now let's say you need to take the thickness of this. We need to take the thickness of this eraser. Right? Then what you do is, now to take thickness, this kind of a rubber object is not recommended because rubber is compressible. No, always when we are using it vernier caliper, we have to use rigid or hard objects. Right? Otherwise, if you need to take a thickness, this is what you can do. See, this is what you can do. Right? And then put on the lock. See, now it is in between the external jaws. Take the reading from here. 1, 3, 6, 7, 18 completed. 18, and from the vernier scale, 7, 18.7 millimeters. 18.7 millimeters. Got it? So likewise, you can use the instrument to take these measurements and compare to the previous instrument, meter ruler, right? This is 10 times accurate because least count of this is 10 times less compared to meter ruler, because least count of the meter ruler was 1 millimeter. Whereas least count of vernier caliper is 0.1 millimeters, right? And there are vernier calipers with least count 0.05, 0.01 also. They are even accurate. They are even more accurate. Right? Then the typical one, that is 0.1. All right. Clear? Raise your hand if it is clear up to this point. About the points we discussed. Now we have discussed up until taking readings. Clear? Right. Good. Okay then. All right. Next thing. Right. Next. Right. Yeah. Okay. All right. All right. Next. Right. Next. The next thing is this. Listen. Next thing is this. Next thing is this. Now, when we try to take readings, right? Now, even though we follow proper methods, right? When taking readings, there can be errors with the instrument. There can be errors in the instrument, or there can be errors with the instrument. There can be errors in the instrument, or there can be errors with the instrument. Right? Last week I discussed the term for that. Right? Errors associated with the instrument are called systematic errors. Right? So the instrument can have systematic errors. Now in the next part, what we are going to see is the systematic errors we have in vernier calipers and how to rectify those errors. Right? Listen. Okay. As the next heading, write down zero errors. Zero errors in vernier caliper. Zero errors. Zero errors in vernier caliper. 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 Right. Listen. Listen now. Listen. Zero errors means if an instrument has an error with the 0 point. 0 point means the initial point. Initial point. We know. Initially, if there's nothing, let me show you from the instrument. If there's nothing kept in between, the external jaws, see, if there's nothing kept in between external jaws, right? When we slide this up until the last point, what happens is these two external jaws are going to be in contact. See, that's the point where it is going to stop sliding. That's the point where it is going to stop sliding. Right? External jaws are going to be in contact, but internal jaws are not in contact. Internal jaws are crossing each other. Can you see? Internal jaws are crossing each other because they are not moving on the same line. See? They are not moving on the same line. Internal jaws are crossing each other. They are crossing each other, but external jaws are in contact. Right? At this point, since nothing is in between the external jaws, right? Since there's nothing is kept in between the external jaws, right? 0 and 0 of the main scale and the vernier scale of the caliper should be coincided. Right? If there's nothing there, there's no reading from the main scale, there's no reading from the vernier scale. Right? There's no reading from the main scale, or there's no reading from the vernier scale, then 0 and 0 should be coincided. Right? If there is coincided as 0 and 0 at this point, there's no error in the instrument because 0 is probably there. 0 is probably there. But there are instruments. Because of several reasons. Right? Even though the external jaws are in contact, 0 and 0 are not coincided. Right? There can be different reasons. We'll explain in the next part. Right? There can be different reasons. Due to various reasons, there are instruments of which now even though the external jaws are in contact, 0 to 0 are not coincided. And which means 0 is not properly coincided. That is called a 0 error. Right? That is called a 0 error. When external jaws are in contact, simple idea is this. When external jaws are in contact, If main scale 0 and vernier scale 0 are coincided, there is no error in the instrument. That is an ideal instrument. That is a correct instrument. That is a proper instrument. That's a correct instrument or an ideal instrument. Right? But when external jaws are in contact, if main scale 0 and vernier scale 0 are not coincided, there is an error in the instrument. That is a zero error in the instrument. Right? That is what we call a zero error. Right? Now let's see what are the zero errors we have and how to find those zero errors. Right. Then, before discussing about the zero error, first we have to know the ideal scenario. No? Ideal scenario means the correct scenario. Right. First, I will show you the correct scenario. Right. Write down. Write down first. Write down below this. When external jaws. Write down. When external jaws. Write down below. When external jaws. When external jaws of vernier caliper. When external jaws of vernier caliper. When external jaws of vernier caliper. When external jaws of vernier caliper are in contact with each other. When external jaws of vernier caliper are in contact with each other. When external jaws of vernier caliper are in contact with each other. If vernier scale 0 and 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 main scale 0, if vernier scale 0 and main scale 0, if vernier scale 0 and main scale 0 coincide each other, coincide each other, there's no zero error, there's no zero error, there's no zero error, there's no zero error in the instrument, 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 there's no zero error in the instrument. Right? Now in that case, this is how the scales are visible. Right, now I'm going to draw only the required part. Right, I'm going to draw only the required part of the scales. Right, see? Now in this case, right, in this case, when these two are in contact, right, when external jaws are in contact, like this, when external jaws are in contact, see, when external jaws are in contact, like this, main scale 0 and vernier scale 0 should be coincided. Main scale 0 and vernier scale 0 should be coincided like this. Main scale 0 and vernier scale 0 should be coincided like this. Right? If they are coincided, there's no error. If they are coincided, there's no error. Right? I just draw only the required part of this scale. Right? If they are coincided, there's no error. This is only a part. Since there is a part, we put this to show that it's a part. It's only a part of this one. Right, take down. Take down, take down. You can draw it with this part also if needed, right? Part is the part of the vernier scale, right? Like this. Right now, in this case, that's a proper instrument, no? That is an ideal instrument, no? That is a correct instrument, no? then in that case, always the apparent reading equals the actual reading. Right? Or the actual reading equals therefore actual reading equals apparent reading. 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 Right? Mention this also. Mention this also. Actual reading is equal to apparent reading. Right? Right. Doesn't know. Doesn't. Now, if there's no zero error, no worries. Our instrument is perfectly fine. Our instrument is perfectly fine. But when we do so, if 0 and 0 are not coincided, then that is where the error comes. Right. Now as next heading write down positive 0 error. Positive 0 error. Next heading. Positive 0 error. Positive. Positive 0 error. Positive 0 error. Positive 0 error. Positive 0 error. Right, listen now. Positive 0 error means this. Right? Now, when we do so, when external jaws of the vernier caliper are in contact with each other, right? Now, 0 and 0 are not coincided. If this 0 is, if vernier scale 0 is right shifted like this, right? When we do so, right, in some instrument, right, when we do so, but right, what we see is vernier scale 0 is right shifted like this. Vernier scale 0 is right shifted like this. Vernier scale 0 is right shifted like this. Then over here. Like this. Like this. Vernier scale 0 is right shifted like this. Now, main scale 0 is somewhere here. Listen, main scale 0 is somewhere here. Alright, let's say main scale 0 is here. And the vernier scale 0 is shifted to right like this. See, like this. Right, that is shifted to right like this. Right, shifted to right like this. To calculate this value, I'm going to draw a amplified view as well, and it is right shifted like this. If this is shifted to right, that is called a positive 0 error. That is called a positive 0 error. What's the reason? Reason is now it is supposed to be at here. 0 and 0 should be coincided. But now, even at the starting point, this is showing a small reading because that is shifted to right. then whatever the reading that you are going to take from the measurement has this small part additional on the reading, right? That is going to measure something additional on the reading. Therefore, that is called the positive zero error. That is called a positive zero error because it is going to measure something additional. No? මෙතනින් පටන් ගන්න ඕන එක්කෙනා මෙතනින් පටන් අරගෙන මේ පැත්තට යන්න ඕන එක්කෙනා දැන් යන්නේ එතන ඉස්සරහින්. Right? It is supposed to start from here, but now vernier scale starts somewhere ahead of what is of the point that is to be somewhere ahead. So that is always going to have a additional reading when we measure something. That's why it is called a positive zero error. That's why it is called a positive zero error. Right? That's called a positive zero error. Right now, to take the reading, let me draw magnified view also. Right? To take the reading, let me draw magnified view of this also. Right? Then say main scale 0 is here. 1, 2, 3, 4, 5 like this main scale. And the vernier scale 0 is shifted to right like this. Shifted to right like this. And one other division will definitely be coincided. Huh? Definitely there is one division. It is coincided here. Right, like this. Like this. Correct. Now the thing is, it is going to read something additional. It's going to read something additional. What we are going to do from our side is, we are going to find that error. Because when the error is known, we can do a correction. We can take a corrective action and correct the error. Now, having an error in the instrument doesn't mean that we need to end up taking a reading with an error. No. We can finally correct the reading when we know the error. That's why we are going to find the error and we are going to correct that error. Alright, now, before you take this down, first write down. When external jaws, write down. When external jaws of vernier caliper, when external jaws of vernier caliper are in contact with each other, if vernier scale 0 if vernier scale 0 is right shifted, 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 if vernier scale 0 is right shifted from main scale 0, right shifted from main scale 0, right shifted from main scale 0, it is called a positive zero error. 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 Positive zero error. All right, now take it down. And when you draw the scales here, the magnified scales, right, it should be exactly as mine because we are going to calculate this error. Right. Take it down. Right. 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 Okay. Now we are going to take this reading. We are going to read this error. We are going to read this error because now it has an initial error. No? It has an initial error. Then, since there is an error, we are going to read that error and going to identify the error, because if the error is known, then only we can do a corrective action. Then only we can take a corrective action. Right? Then this is how positive zero error is read. See, listen. This is how positive zero error is read. Positive zero error is read as number of coincided division. Number of coincided division times least count. Positive zero error is read as number of coincided division times least count. Number of coincided division times least count. Right? Now, if I take the error of this given case, right? Positive zero error. Number of coincided division 1, 2, 3. 3. Please count 0.1 millimeters. Then this is 0.3 millimeters. 0.3 millimeters. Which means this instrument has a positive error of 0.3 millimeters. Idea is, in each and every reading that we are going to take out or take from the instrument, from this caliber, right, it reads 0.3 millimeters additional to what we have to read. Right? It is reading 0.3 millimeters additional to what we have to read. Since there is an additional reading, we can subtract that from the final reading and do a corrective action. We can take a corrective action. Right? So, since we are subtracting this additional reading from the final reading, that is called a negative correction. Since we are subtracting this from the final reading, because this is something additional, something extra is read here. Therefore, it is subtracted from the final reading. That is called a negative correction. Then for positive errors, we do negative corrections. For positive errors, we do negative corrections. Right? Okay, first read the error. Right there. Right there. Highlight the equation like this. Highlight the equation and then right here. Positive zero is number of coincident divisions 1, 2, 3. It will count 0.1 then 0.3 millimeters. Right. Okay, write down below with the red pen. Mention below with the red pen. Mention below with the red pen. For negative correction, right? Mention below in red. For negative correction, negative correction, within brackets, subtracting within brackets, subtracting the value of positive zero error. 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 Close brackets. Close brackets. Should be done. Should be done. Should be done. For each reading. Should be done for each reading. Should be done for each reading. Should be done for each reading at the end. Should be done for each reading at the end. Should be done for each reading at the end. Should be done for each reading at the end. Right. Now in that case it is like this. Actual reading is not equal to apparent reading now. Then from the apparent reading means the row reading. Apparent means what is visible. Row reading, row 1. Without doing any corrections. Row reading. Then apparent reading minus positive 0 error. Mention this below. Therefore, actual reading is apparent reading minus positive 0 error. This is called a negative correction. Right? Alright? Visible reading again, positive correction, positive reading again, positive error again. Subtract the right? That is called a negative correction. Right? Because we were reading additional 0.3 millimeters, it should be subtracted. It should be subtracted. Right? Actual reading equals apparent reading minus positive 0 error. Right? Actual reading is apparent minus positive 0 error. Right? Then let's move on. The next type of the error, negative 0 error. Next heading, negative 0 error. Next heading, negative 0 error. Negative 0 error. Negative 0 error. Right. See. Now you can guess what is to come as negative 0 error. Right, in negative 0 error, what happens is when external jaws are in contact, right? When external jaws are in contact, vernier 0 is shifted to left. Right? Vernier 0 is shifted to left. Right. See? In that case, the opposite of the positive 0 error. Then in this case, vernier 0 is shifted to left. vernier 0 is shifted to left of the main scale 0. Shift to left of the main scale 0. Like this. Right now, vernier scale 0 shifted to left. Right? And if I draw it here like this, vernier scale 0 is shifted to left. Vernier scale 0 is shifted to left. Right? Okay. See, it is like this. Like this. Now, in this case, the opposite of that is shifted to left. If there is shifted to left, now what's the impact? What's the impact? Supposed to start from here. It is supposed to start from here. Supposed to start from here. Here to the right. But now it is starting behind the supposed point. It is starting behind the supposed point. Starting behind the supposed point means always the reading is short. Right? Always the reading is short now from the actual reading. Since the reading is short now, that is called a negative error. That's a shorter reading. In the previous case, it was an additional reading, an extra reading. Now, in this case, there is a shorter reading. There is a shorter reading because 0 is supposed to start from here, but now it starts somewhere behind that point. So it is always behind when taking a reading. That is called a negative error, negative 0 error. Right. Take down. Before take down. I will even write down. When external jaws write down. When external jaws of vernier caliper are in contact with each other, when external jaws of vernier caliper are in contact with each other, when external jaws of vernier caliper are in contact with each other, when external jaws of vernier caliper are in contact with each other, when external jaws of vernier caliper are in contact with each other, if vernier scale 0 is left shifted like this, if vernier scale 0 is left shifted, if vernier scale 0 is left shifted, if vernier scale 0 is left shifted, if vernier scale 0 is left shifted from main scale 0, left shifted from main scale 0, if vernier scale 0 is left shifted from main scale 0, it is called a negative 0 error. It is called a negative 0 error. Right? It is called a negative 0 error. It is called a negative 0 error. It is called a negative 0 error. Negative 0 error. Right? I couldn't tell you before. Now in the previous one we wrote, right? You have to underline or highlight in the previous one. In the previous one, you have to underline or highlight right shifted and positive 0 error. In the previous one, highlight right shifted and positive 0 error. Right shifted and positive 0 error. And in this one, highlight left shifted and negative 0 error. Right? Left shifted and negative 0 error. Right, yeah, highlight color. Right, now take down the diagram. Take down the diagram. Take down the diagram. Diagram. Take down the diagram. Right, take down the diagram. Right. Okay, finished. Finished. Listen now. This is how the negative zero array is read. This is how the negative zero array is read. Right? Now, when scales are moving in the opposite direction, right, there's a small difference. That is this. Negative zero error. Negative zero error is read as, right? That is total minus coincided. Total minus coincided number of divisions. Number of coincided division times least count. Right? This difference is always there when scales are moving in the opposite direction. Scales are moving in the opposite direction or reverse direction, then total minus coincided. Negative zero is written as, is read as this. Right? Take down the equation and highlight. Take down the equation and highlight. Take down the equation and highlight. Right, that is read as this. Now we can read out the reading here. See, we can read out the reading here. Negative zero error. Total 10. Total number of divisions in vernier scale 10. Right, 10 minus number of coincided divisions. Right, ninth one is coincided. Can you see? Right, ninth one is coincided. Right. Wait, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ninth one is coincided. Right, ninth one is coincided. Then 10 minus coincided 9. Into least count 0.1 millimeters. Then the error here is 0.1. 10 minus 9 is 1 of 10.1 millimeters. Zero error in this instrument is 0.1 millimeters. Then what's the idea? In each and every reading you are going to take from this instrument, that is 0.1 millimeters short. That is 0.1 millimeters short from the actual reading. Then if you need to get the actual reading, that 0.1 should be added. That is called a positive correction. That is called a positive correction. Right. First, take the error. Take the error. Right. Take the error. And you have to keep these equations in mind. Should be able to recall. Should be able to memorize. Right. Should be able to memorize. Take out. Okay. Right. Then mention below. Mention below. In red. A positive correction. Right now we have to add no. That is called a positive correction. A positive correction. A positive correction. Positive. A positive correction. A positive correction within brackets. Within brackets. Adding the value of negative zero error. A positive correction within brackets. Within brackets. Adding the value of within brackets. Adding the value of. Adding the value of. Adding the value of negative zero error. Adding the value of negative zero error. Adding the value of negative zero error. Positive correction. Adding the value of negative zero error. Close brackets. Should be done. Should be done. For each reading at the end. Should be done for each reading at the end. Should be done for each reading at the end. Should be done for each reading at the end. Right? Now, here, the actual reading is apparent reading plus we are going to add this negative zero error. The actual reading is apparent reading plus negative zero error. Right? Actual reading is apparent reading plus negative zero error. Mention this below. Mention this below. This one. Right? So with that we have come to the end of vernier caliper. That is the end of vernier caliper. Right? That's everything. That's everything you need to know. Right? And about zero errors. Right? This is how the zero error is checked without keeping anything in between. Without keeping anything in between. Right? Make it in contact. Make external joint in contact. And then you have to check whether main scale 0 and vernier scale 0 are coincided like this. You have to check whether main scale 0 and vernier scale 0 are coincided. Now in this one, in this particular one, right, they are coincided, right? In this particular one, they are coincided, right? Yeah. In this particular instrument, there is no error. In this particular instrument, there is no error. That is how the error is checked, right? And about the reasons, right? One reasons can be given. About the reasons for positive zero errors and negative zero errors. Positive zero errors are usually because of corrosion. Corrosion means now they are iron plates, no? They are iron. They are iron, no metal. Iron means metal actually. They are metal. Then sometimes when we use this for a longer time, right? These parts are getting corroded. These parts are getting corroded. The nuts and these iron parts, right? Now even in my one, the small corrosion is coming, right? So these parts are getting corroded, right? Corrosion, right? They are getting corroded. Corrosion again. Then what happens is, right? Small corrosion particles are here. Then the zero is not going to coincide and it is right shifted. So therefore, the common reason for positive zero errors, is corrosion, right? Common reason for positive zero errors is corrosion. And about the negative zero errors, right now when we use this for a longer time, high duration, right? Now always when we use this, always external are going to be in contact when we are checking errors and using them. Then over time, gradually, these sites are getting wear and tear. Given again, wear and tear, right? They will undergo wear and tear. It's going to decay, right? By a small bit, right? Even by a small bit, it matters because our least count here is only 0.1 millimeters. Not even a millimeter, that is 0.1 millimeters. 0.1, right? So therefore, even though that's a small error, it matters. Then for the negative zero errors, the common reason is wear and tear of the material. Right? Wear and tear of the material is the common reason for negative zero errors. Right? So that's how the errors occur. And when you identify the error, right? When you identify the error, then no need to worry about the reading because when you identify the error, then you can take a corrective action and you can make it correct. You can take a corrective action and you can make it correct. Correct? You can take a corrective action and you can make it correct. Right? That's how we deal with the erroneous instruments. Instruments. Alright. Then with that we have come to the end of today's discussion about vernier caliper. Right? That is simply the end of vernier caliper. And next week we are starting micrometer screw gauge. Right? Next week plan is this. Next week we are starting the micrometer screw gauge. Third out of five instruments we have micrometer screw gauge. Right? So next week we'll be covering micrometer screw gauge. Right? Again, on the same day itself, we'll cover micrometer screw gauge. Right? And I will give you an example question on vernier caliper next week, right? To practice questions. Otherwise, our main part to be covered in the next class is micrometer screw gauge. Alright. Raise your hand if everything is clear, and you can ask if there's anything to clarify from my side before we wrap up. Right now, it's your time. Clear. If anything to know about this, you can ask now. Right. Means all clear. What about the ones on YouTube? Are you also okay? If there are any questions, anything, right? Feel free to ask anything. If no questions, we can wind up. Right? I'm just waiting if you have any questions. Any questions or any clarifications? Clarifications needed? Understood. Right, good. Right. The ones who join the class, new, right? Please make sure your addresses are correct on the LMS because that will be the same address we'll be using when posting dudes, right? That will be the same address we'll be using when posting dudes. So please make sure that they are correct on the LMS. Right. Okay, then if no questions, we can wind up. All right. Then that's it for vernier caliper. We wind up. Stay safe and work hard. Because A-level is always a consistent effort, right? Now, don't think that you are 28 batch and you have 2 more years. No, don't think that way, right? Now, that doesn't matter even if that's a small amount, as long as you are consistent, right? Doesn't matter whether that's a small amount. You should be consistent, right? So work hard, and stay safe. See you in the next class. Good night and goodbye. See you.